Step 2, the final step in the forward kinematics is the following. In forward kinematics, we are given the values of the joint variables and we are given the mechanism parameters. Because we know them, because these are fixed on the bodies, we can find out the relationship between this and this, this and this, and this and this. They are nothing but the transformation matrix from 2 to 1, 3 to 2, and 4 to 3. Then using chain rule, just by multiplying them out, we get the transformation matrix from 4 to 1. Transformation matrix from 4 to 1 is nothing but the position and orientation of the last body with respect to the first. And that is exactly what we wanted. What is the position and orientation of the last body, the end vector, with respect to the first body? So it is solved as simply as this. Just multiply this out. Construct them, calculate them numerically, then simply multiply them out, you get this. Okay? So the forward problem is as simple. Of course, we have now stated how these have to be fixed. How do we define joint variables and mechanism parameters? We need to do that. But before that, the inverse problem will be solved similarly. So the step 2, the first step is there. The next step after fixing, we are in the inverse problem, we are given the position and orientation of 4 with respect to 1. So transformation matrix 4 with respect to 1 is given to us numerically. And we can, using this kind of an expression, because these are in terms of the joint variables and the fixed parameters, we can actually multiply them out algebraically, and we are going to do something like that. And then get an expression for the numerical values of these. Okay? So we have a relationship between the joint variables and we end up with a relationship between the joint variables. There are 12 such relations. Okay? In this case, we have to find the values of 3 joint variables. In our 6th degree of freedom case, which we will solve as an example, we need to find 6 of them out of 12 relations. Okay? That is something we are going to do. So this is the approach for solving the forward and inverse kinematic problems. Now let us look at the problem of fixing these reference frames and defining joint variables and mechanism parameters. So again, let us look at the same mechanism. Okay, 3 joints, prismatic in the middle and revolute at the end. So we are now looking at how to represent the mechanism or define the variables, the parameters. So the approach was the first paper in this approach, okay, that we are going to elaborate is by Dimenberg, and others followed that later. The approach is the following. First, you fix joint axes. So here we consider only mechanisms with revolute and prismatic joints, and in this case only serial chains, which are almost the simplest ones. Okay. Although serial chains by themselves are simple, the problem of finding the joint variables given force of 4 with respect to 1 is a very tough problem for the general mechanism. For special mechanisms, it turned out to be fairly simple. That is what we are going to see. Now you fix joint axes. So you have these joint axes which are fixed to each joint. By the way, prismatic joint doesn't have a joint axis. It has only a joint direction, but still assume that we have a physical prismatic joint, we will put an axis through the center of that. Okay? Whereas revolute joints have joint axis. So you fix joint axis, and then these are the physical links. Okay? These are the physical links because of a certain necessity of design of the mechanism. But if you ask the question, for exactly the same kinematic performance of the mechanism, motion of the mechanism, you could really have other links actually starting from here and going around like this and connected here. You could have several physical ways of connecting the joints or between the joints. The minimal way of doing it is what Dimenberg came out with. He said, consider links to be, okay, as the common normal between the joints. So this is a joint and this is a joint axis, this is a joint axis. These are lines in space, skew lines in space. Okay? Now, when there are 2 skew lines in space, there is a common normal between them. Okay? If they are parallel, there are an infinity of common normals. If they are not parallel, there is a unique common normal between them. So that unique line you consider to be in place of this physical link. So replace the physical link by this common normal. Okay? This is mathematically very elegant and actually enables us to do the mathematics very quickly. And so between this joint and this joint, this is the common normal. So instead of this link, we'll consider this. Okay? This is a very big simplification which happens. Now, in a revolute joint, you look at this particular, okay, consider this joint. Okay, the motion of that joint takes place by motion of these two links. Okay, use a revolute joint. Since we have replaced this by this and this by this, the motion of the links is the rotation of this with respect to this about this revolute joint axis, and this is perpendicular to this axis. This is perpendicular to this axis. So imagine there is an axis and there are two perpendicular lines coming out of them. They rotate with respect to each other. That is the revolute joint motion. Similarly, if it is a prismatic joint, these two cannot rotate with respect to each other. They can move along this axis with respect to each other. So the translation of this with respect to this along this axis will be the prismatic joint motion in the case of a prismatic joint. Okay? So we are simplifying things in this representation. Now let us come to the more precise definition of these quantities. One more. Okay. So these were the joint axes that we selected, and these are the links now. Note that I have replaced the physical links by these things. So physical links are no more there. Now you have the joint axis. The joint axis can be given a direction. This could be arbitrary. It could be in this direction or could have been in this direction. That's for us to choose. Okay. Now, we can have conventions in different ways. So link K, take this link 2, is between joint 1 and joint 3. So as joint 2. So this joint 2, this joint 1. So link 2 is from link joint 1. Sorry, this is link 2, and this is joint 1 and this is joint 2. Link 2 is from joint 1 to joint 2. Similarly, link 3 is from joint 2 to joint 3. This is a convention. You could have done it other anyway. This is a convention we are going to use. Okay, and and then the additional thing is that how do we fix the critical thing is how do we fix axes in a standard way, the reference frames to links. So what Denavit and Hardenberg, who followed Dimmenberg's approach, suggested was this: let the x-axis which is fixed to 2, okay, link 2, be fixed along the link. Now the link is just a common normal, so that is the axis, and x2 axis extends beyond that, beyond joint 2. Okay, and then look at this z2 axis and the x2 axis. This is the reference frame which is fixed to link 2. Similarly, this is the reference frame. This is the reference frame which is fixed to link 3, that is x3 and z3. You can of course ask where y3 is. Y3 is the cross product of z3 and x3. So it's very easy to get. Once we have two of them, finding the other is a very simple matter. So this is how you fix reference frames. Now this looks a little odd. This reference frame on 2 is fixed at the end of the link. Okay, it is fixed to the link at the end of the link. And this reference frame also is fixed to the end of the link. Okay, that is the way we fix reference frame in a standard way. Now look at the joint parameters. Okay. Now associated with the link there are two, not joint parameters, the parameters of the mechanism. Associated with the link there are two fixed parameters. One is the length of the link, which is this, and the other is the twist of the link. Okay, this is true only for a binary link or a link with two joints. It has to be defined for other links, but consider this symbol link. So this is one link with two joints. The angle between the two joints at the end of the link gives the twist of the link. Okay, they are called A and alpha. So mathematically you can regard this AK and alpha K as follows, or A2 and alpha 2 as follows. The translation you have to give to 1, Z1, along X2 to make it coincide with Z2. You have to translate it by this much, and you have to rotate it by a certain amount in order to make this coincide with this. Okay? That is the operation you have to imagine for defining alpha A and alpha. Similarly, at the joint you have two parameters. One is called the offset of the joint called dk, which is the distance between this point and this point. That is, along this axis there are two common normals which join them. There are two links on them. The distance between the two links is called the joint offset, and that's called d. And the angle between these two, okay, the two x-axis on the z joint is called the theta, the angle of the joint angle. So remember, in a prismatic joint, theta is fixed and d varies. In a revolute joint, d is fixed and theta varies. Okay. So this is the way we define it. By the way, I'll give this to the organizers, and hopefully you will get the notes with you. So even if you don't follow exactly, follow the concept. Okay, the details you can look up when you get the notes. Now let us apply this to perhaps the most complex manipulator out of 6 degree of freedom manipulator serial chain that you will see. Not the most complex, but simply in some ways. But in terms of the number of joints, this is usually the most complex 6 degree of freedom manipulator. This is the 6th revolute manipulator. Okay, we will now fix access to this 6th revolute manipulator and define the and see what the variables are, the parameters are. Okay, so then let me describe the manipulator. So there is this base which is in black color. This is link 1. The second link is in blue, and that rotates about an axis through this. So about a vertical axis. So on this link 2, there is a revolute joint which is horizontal, and on that between this red link and this particular blue link. So you can regard this as a shoulder and this as an upper arm. Okay, so this is the shoulder where there are two joints, and this is the upper arm, and this is the lower arm. Okay, so between this and this there is a horizontal joint, revolute joint, and this rotates with respect to this about this joint. So the blue link is there. The blue link is the lower arm. Now you have the wrist. Wrist has 3 joints. So this is what is called a concurrent joint. The 3 joints are this revolute joint, and this revolute joint. All of them, whatever be the rotation of the joints, the axes of the 3 joints are concurrent, and that they meet here. Okay, so between this blue link, which is the lower arm, and the red link, there is a revolute joint along this axis. Between this red link and the next blue link, there is this joint which has this particular axis. This is a revolute joint. And between the blue link and the last link, which is 7, there is a revolute joint along this, and I have shown a gripper here. Okay. Now, if you fix the reference frames based on the convention that we saw earlier, okay, we fix the joint axis, Z axis along the joint axis. So Z1, Z2, Z3, Z4, that is for this joint, Z5 along this joint, and Z6 along this joint. Okay, and you can check. I will give this note to you. You can check whether x-axis have been correctly fixed based on the convention that was described in the last slide. Okay, I don't want to get into details of that. That will take time. Now the parameters have to be defined. So it turns out that so in this manipulator, many things have been simplified actually. If you look at the link lengths, okay, although you can see this length, this length, this length, this length, and this length as physical length, kinematically, the way we define things, there is only one length which is non-zero. Rest of them are 0. Okay, there is just one length, that is A3 or link 3, which is non-zero, rest of them are zero. But that has to be taken along with the joint offset. Out of the 6 joint offsets, 2 are zero. There are 4 of them which are non-zero. Okay? So although many of the link lengths are zero, many of the joint offsets are non-zero. Now the twist of the link, that is the angle between the 2 joints of a single link, are actually special values. That is 90, 0, 90, 90, 90 and 0 degrees. These are n degrees. These are special values. So let me say something. If you simply randomize these numbers, okay, these numbers, suppose you give random values, it is next to impossible to do the inverse calculation. It is because these are these simple values that we are able to come to certain simple relations for the inverse kinematic relation. Okay? This arbitrary values for this and doing the inverse kinematic was called the Mount Everest problem. One of the top kinematicians, his name is Prudenstein. Even at the BTech level, you must have come across his equation. So he called it the Mount Everest problem, but that was solved to some extent by some people later. But for this simple manipulator, this is not that difficult to solve. So this is an example how we apply the convention we saw earlier of fixing reference frames and defining the parameters for this mechanism. And this among the manipulators that we typically see, serial chains, this is actually the more complex one. Now let us, before we go to the inverse and forward calculation, let us also look at the transformation matrix or the pose matrix. Basically the transformation between adjacent reference frames. So what is the position and orientation of this particular reference frame with respect to this reference frame as a function of the mechanism parameters. Okay, this is something important to develop. And if you look at this being the reference frame on the previous link, and this on the current link, and this the next link, that is x, z, and I haven't shown y. The parameters are this joint angle theta I, this length di between these 2 links, and then along the link a I plus 1, the length of this link, my script doesn't work. Yeah, thanks. So between this joint and this joint, this length a I plus 1, and the angle between this and this, alpha I plus 1, that is here, are the parameters. And you can derive that the position of this with respect to this can be obtained by this. This capital C and capital S stand for cos and sine, cosine and sine. Okay? And then the rotation matrix I plus 1 with respect to y can be obtained through this operation and can be obtained at this matrix. Now this looks a little formidable because the terms are a little involved. This is reasonably simple, but when you apply this to our manipulator, which we saw earlier, everything turns out to be very simple. The offset of the origin of the reference frames, okay, are simply 0, 0 di or 0, 0, 0, or just for one joint, which is the second joint, it is this quantity. Otherwise, this turns out to be very simple. Okay, so all of the calculations are going to be fairly simple. Similarly, the rotation matrix takes certain very simple standard form because we have value of alpha I plus 1 as 0 or 90. Then immediately this takes very simple form. Okay, so within 1, 3, 4, and 5, it is as similar as this, and for 2 and 6, it is this. You can actually check it out for that particular manipulator. So the transformation matrices of this, the translation part and the rotation part of the position and the orientation are this symbol for that particular manipulator between the adjacent reference frames. Now the solution to the forward problem is very, very straightforward and trivial. So this is our mechanism, the manipulator. In the forward problem, remember, we are given the angle between angle at all the joints, this joint, this joint, this joint, all the 6 joints. Okay. Since we are given the angles and since we know the fixed parameters, we can construct the values of this. Okay, the numerical values of those are very easy to calculate. And all you need to do is multiply them in chain to get the transformation matrix between 7 and 1, which is nothing but the position and orientation of the last link with respect to the first. So that is the forward problem, and it is solved as easily as this. Okay, for this particular mechanism, it is very trivial. For any open chain, it is very trivial to do the forward calculation. Inverse is tough, it is not simple. So let us start with the inverse. So this is a manipulator. I have shown it in a slightly different position. I have rotated this particular joint a little bit to show this not aligned like this but at an angle. Now the most crucial observation which makes all our calculations very simple is the fact that we have this particular point, which I am now calling capital C, as the point of concurrency of the wrist. Okay, this is the point of concurrency of the wrist. Now, whatever you do to the last 3 joints, however much you rotate them, okay, this particular point is the intersection between the axes, and all these 3 axes remain intersected at a point. Okay, because of that, it turns out to be this particular point of concurrency is a fixed point on the last link. It is a fixed point on the last link. Okay, so it is a point, it can be regarded as a point of the last link. Now, if we are given the position and orientation of the last link with respect to the first link, the position of any point on that can be obtained numerically. So the position of C can be obtained numerically from this particular position and orientation of the last link, and the position of this in the last link, because that is a fixed thing, that doesn't change, however much the mechanism moves. Okay, and then this particular point, okay, this particular point, its position in the first base, in the base coordinate frame, can be obtained purely as a function of this joint angle, this joint angle, and this joint angle. Okay, it is a function of purely those 3 joint angles. It is because this is a point of concurrency, otherwise this wouldn't have happened. So what it amounts to is that the numerical values of the position of C in the global frame, that is on the left hand side, and on the right hand side are expressions for each of these terms in terms of the joint angles θ1, θ2 and θ3. That and the fixed parameters are all that is there in this relationship. This relationship comes purely from multiplying the first 3 coordinate transforms. Okay, that is how we get this. And this we obtain from T7 with respect to 1 using that position relation that I had shown earlier. So this is the key relation that we are going to use in order to get θ1, θ2 and θ3. Okay, so we know these 3 numerically and we have expressions for them. So this is the relation. So second step that we are going to do, this can be done in several ways. I am just showing one way of doing it. And what is important is to interpret our results. Okay, that is more important than getting the results. It has to be correct. It has to be interpreted correctly. So now, look at this particular relation. Look at this particular term. That is happening in both these particular equations. By the way, there are 3 equations in this equation. This is a vector equation, 3 equations. So in the first 2 equations, these terms are common. So I can eliminate them. Okay, I can eliminate those terms, and if I eliminate those terms, I get one equation. I use one equation to eliminate and put it in the other equation. So I eliminate θ2 and θ3, end up with a relation only in θ1 and only θ1, a single equation in θ2. Okay. Now I can do some manipulations of that. This is something you need to do yourself, and then you come out with this relation. theta 1 turns out to be simply this particular thing. Tan inverse of yc by xc. Yc and xc are available here numerically. So you have this numerically. Okay? And then sine inverse of these quantities. This is a fixed parameters d3, and xc and yc are already here. It is as simple as that. Okay? The value of theta 1 can be obtained as simply as this. We need to, of course, calculate xc, yc, zc, and we know d3, and from that we can get this. Now let us look at this relation a little more. Tan inverse of a ratio, is this well defined? How many solutions are there? And is it well defined? How many solutions are for tan inverse of some argument? There are two solutions, right? If you take tan inverse of something, there are two angles which come out as a solution except for a special case. Okay? So are there two solutions here? The answer is no. There is only a unique solution here. Because you know yc and xc, the two coordinates we are using to find that angle separately. Because we know this separately, we know in which quadrant the angle is, and because of that we can calculate it uniquely and not as one or two angles. So there is a unique solution for this. The only case where this is not defined is when both are 0. When both are 0, this is not defined. Okay? And what is meant by both being 0, xc and yc being 0? We go back to our mechanism. This is the point C. What is meant by xc, yc being 0? What is meant by that is this particular point coincides with this angle, this particular axis. And that is what is meant by xc, yc being 0. It coincides with this central axis. When it coincides with this central axis, actually the angle, the angle that we are talking about, theta 1, is an angle made by, so take this point, project that point onto, perpendicularly onto this axis, look at the whole thing in the direction of this axis, you see a line, the direction of that line in the global x1, y1 reference plane is the angle theta 1 that we are talking about. Okay? And that cannot be defined when this is actually coinciding with this. There is no angle to talk about. All angles are equally correct. So physically, that's what it means. But the more important thing is this. Okay? So here, when is sine inverse defined? Sine inverse is defined only when the argument is between -1 and +1. Sine cannot take, sine of an angle cannot take a value above 1 or below -1. So if the angle turns out to be, if this argument turns out to be above 1 or below -1, this thing is not defined at all. Okay? So otherwise, if it is defined, if it is not +1 or -1, if it is between those two values, then there are two solutions for a sine inverse, an angle and phi minus that angle. So this calculation has two solutions, both are equally valid. This is something you have to remember, both solutions are equally valid. Now let us look at the interpretation of these statements I made, that what is meant by this going outside the bounds, sorry, and what is meant by two solutions for this. Okay? Now if you look at our manipulator from above, this is the point C, this is exactly what we will see sorry, when we look at the manipulator from above. I should have drawn that manipulator here. So we are looking actually at this particular point, and we are looking in this direction. This is the x-axis, y-axis also will be horizontal, and we are projecting this line, and this line onto that xy plane. This is x and y is also x. And so what we see is here. What we see is this. This is upper arm and this is the lower arm. This is the wrist. The upper arm and the lower arm are offset in the previous one. So there is this particular offset. And that we see fully in the xy plane. The angle θ1 that we are talking about is this angle. Okay? This tan inverse yc by c is actually, you take the point C and join it with a line to the center. Okay? The angle made by that line, okay, I haven't drawn it here, is this particular angle. This angle comes from actually the triangle, which is two triangles you can see as I draw this line between this and this. So this particular angle is this angle. Now, what is meant by the fact that this is above 1 or minus 1? What is meant by that is that C cannot reach the specification that you have demanded. Okay? What is meant by that? What is meant by that geometrically is that when you calculate xc, yc, zc based on the transformation of the 7th link with respect to 1 and the position of that C with respect to the last link, you get the position of C numerically. If that turns out to be inside this circle, okay, inside this circle, then this point C can never reach inside that. The wrist can never reach inside that. That radius of the circle is nothing but this offset. Okay? Geometrically, physically, that's what it means. The fact that we don't have a solution here means that our specification of the inverse dynamics problem has put C within the circle. And so we cannot reach it. Okay? And what is meant by two solutions? This is another thing you have to understand. What is meant by two solutions is that given any location of C, that can be reached with two values of θ1, one like this, and then you turn it around, okay, and you turn the manipulator backwards, you can reach it in another way. Okay, it's somewhat like this. So I am reaching something here like this, okay, and then I can do that by turning, okay, and moving my, turning and moving my arm like this. So my body has turned to two different angles in this. One is like this, the other I turn around and do like this. But I reach the same spot. Okay? That is the meaning of these different angles, different values, the two solutions you get out of this. Okay. So this physical interpretation is very important for you to figure out and understand what is really happening. Now let's look at the calculation of angle θ2. Okay? Calculation of angle θ2 is actually fairly reasonably simple. You look at this manipulator in the other direction. So when you look at it from above, you see these two, the upper arm and the lower arm. Suppose I look at it in this direction, that is in the direction of this line. Okay? What I see is what I have drawn here. Okay? This coordinate R1, okay, is along this direction. R1 is along this direction. Then Z is out of the plane. Z1 is out of the plane, so Z1 is there. In this projection, you see the lower arm and the upper arm like this. Okay? And the two angles you are seeking are θ2 is this and θ3 is the angle between extension of this and this line. Physically, that is what you are seeing. Okay? And so you can calculate θ2 from this equation. Okay? So I have given an expression for this with various values. All these are calculatable. So basically, θ2 turns out to be tan inverse of some E2 by E1 minus cos inverse of some E3, which is defined here by this. Okay, so this tan inverse, again, whether this will be fully defined, you have to understand whether that happens or not. When both are 0, okay, E2 and E1 are 0, then C turns out to be at this particular point. Okay, what it means is that any value of theta 2 will satisfy the equations. But here comes the other part. This can have value above 1 or below -1, or could be in between. And what is meant by that? So when it is above 1 or below -1, what means is that the point C cannot attain the specified location again, but in this projection. Okay. Now, if you look at this mechanism, consider this to be a mechanism, and ask the question: when I rotate these two joints, where all can point C reach? What is the answer to that? This is a two-arm mechanism, three-link mechanism, two revolute joints, serial chain. One link is this, the other link is this. I simply rotate this fully and simply rotate this fully. I take C2 all possible positions. What is the geometry of that set of points? It turns out to be something very simple. It is the annulus of the circle. There is an outer circle and there is an inner circle. Okay? Between these two circles, there is an annular region which can be reached by the point C. What is the outer circle radius? The outer circle radius is the length of this plus the length of this. Can it reach beyond that? It cannot reach beyond that. Okay? Similarly, if you fold it up, rotate it and make the angle 180 degrees here, then C you can find cannot reach closer to the origin beyond a certain point. Okay? That is given by the length of this minus the length of this, or if this is longer, the length of this minus the length of this. So there is an inner region where it cannot reach, and there is an outer region where it cannot reach. The value here going above 1 or below -1 means this. Okay? It cannot reach the given positions. Okay? What is meant by the fact that there are two solutions? The meaning of two solutions is this particular point can be reached with two values of theta 2 and theta 3 also. Okay? One is with this, and the other is actually with this link like this and this link like this. So that can be easily demonstrated. I want to reach a position like this. So the manipulator I am talking about is like my upper arm and lower arm. Okay. I want to reach this. I can do it like this, or I can reach this position like this. This is called the elbow down position, and this is called the elbow up position. In these cases, the angle made by my upper arm and lower arm are different. Okay. So the two solutions coming out of this for theta 2 are geometrically precisely this: the elbow down position and the elbow up position. And this, of course, is well defined, and you know the quadrant. There is only one solution. You know E1 and E2 separately, so you know what this angle is for. And the third angle. So for the previous angle theta 1, there are two solutions. You take that any of the angles values you got for theta 1 and substitute into these equations to get this. Okay, there are two solutions here again. So altogether there are four solutions now. All four are equally valid if the joints can take any values desired. Okay, but that is not the case always. What about our elbow? Can it rotate through 360 degrees? Well, you can do it, you have to break it. So otherwise there is a limit to the position that it can attain. So similarly, in a typical robot, those limitations are there. So when I say there are four solutions, it is subject to these limitations. Now let us look at the last joint, that is theta 3. We have already got theta 1 and theta 2. Numerically, there are four solutions. take one combination of values and then you can calculate theta 3 uniquely using a simple tan inverse term and subtracting this theta 2. So this is fully defined, okay, unless again both turn out to be 0, in which case it's not defined. Otherwise it is fully defined. So you get the angle uniquely. So for a combination of theta 2 and theta 1, there is a unique value for theta 3. So right now altogether for the 3 angles there are 4 sets of solutions. Okay, and the geometrical meaning of the being solutions and the not being solutions are precisely what I have described. And what I described is for the 6R manipulator. Okay. Now what about the remaining angles? There are actually 6 angles. We now calculated or found expressions for theta 1, theta 2 and theta 3. There are theta 4, theta 5 and theta 6. So that can be, I am just giving you an overall scheme for calculating this. I have given the algorithm here, but this is the approach. So theta 4, theta 5 and theta 6, okay, are obtained as follows. If you are able to have numerical values for this rotation matrix 4 to 1, which is made up of multiplying 3 rotation matrices, one more. If you are able to have values for this rotation matrix, which is 7 with respect to 4, which comes out of the last 3 rotation matrices, which involves theta 4, theta 5 and theta 6. You can also find expressions for the elements of this rotation matrix in terms of theta 4, theta 5 and theta 6. Now this can be obtained numerically very easily because we already know, okay, I haven't done it correctly. This is actually R7 with respect to 1. Okay, R7 with respect to 1 we know because we are given the end-effector orientation. And this is R4 with respect to 1, which is numerically calculated from theta 1, theta 2 and theta 3. We have already calculated those. So this can be calculated numerically. So take transpose of that, post multiply it with R7 to 1, you get R7 to 4. Okay, and so we got it numerically, and we can obtain this in terms of angle theta 4, theta 5 and theta 6 by multiplying those rotation matrices R5 to 4, R6 to 5 and R7 to 6, and so you get the expression for these elements. So now you have basically 9 elements from which you have to find 3 angles, and it turns out that if you have done the similar calculation of Euler angles, it turns out that there are 2 solutions, because not in all cases, but in general there are 2 solutions. And so you get for this also, you get 2 solutions. So altogether there are 8 solutions for theta 1 to theta 6. Okay. So the algorithm for calculating this, I suggest that you write yourself. You find out the expression for this by keeping these as variables. Find out the expression for the manipulator that we have seen, and then you will be able to figure out a way of corresponding this with an expression, an algorithm for calculating theta 4, theta 5 and theta 6. That is not very difficult. Okay. It turns out to be simple. To give you one input, it will turn out that theta 5, there will be one term in this 9 by 9 terms here, 9 elements here, which is simply either cos theta 5 or sin theta 5. Just one element will be that. And using that you can get 2 values for theta 5. Okay, there are cases where there are only one value, but in general there are 2 values. So you can get 2 values out of that. Using any one of those values, you can get unique values for theta 4 and theta 6. That is the way the calculation will progress. Okay. So this is the calculation, the inverse calculation for the 6R manipulator, which I said is one of the more complex manipulators that are typically used industrially. But if you ask the question, if you have a general manipulator with alphas and those things non-90 and non-0, then this is very difficult to calculate. But you don't have to go that far. Take a very simple case of the wrist not being concurrent. Okay? Let's assume there is just one offset in that wrist and it doesn't make it concurrent. You cannot do this. Okay? It becomes significantly more complex. So for a concurrent wrist manipulator with of this type, it is not all that difficult to calculate. But what I want you to take out of this are some of the concepts that we have developed. Some of the concepts that we have seen. One, how to define rigid body orientation and position or pose using the transformation matrices or the rotation matrix and the offset. How to fix a standard way of fixing reference frames to serial chains with revolute and prismatic joints. A standard way of defining the parameters of the mechanism, the fixed parameters and the joint parameters. Okay. And applying it to a typical manipulator like this, and one typical way of solving. But in all this, there are many different ways of doing this. The representation can be different. The way of fixing reference frames can be different. The way of defining the fixed parameters and the joint parameters can be different. The way of finally solving and getting the solution can be different. So if you read different papers and different books, you may find different ways of doing this. Okay? You have to know at least one correct way of doing it. And one of the most important things in solving is to interpret your final results, to be able to understand physically what it means. Okay? So with that, I will close the talk. Thank you. So, questions? Yeah.
You explained that way of attaching frames using dynamic is minimal representation. Can you explain it in this case?
Not attaching frames. Actually, Devenberg's representation of mechanism is substantially minimal. So what I meant by that is the following. If you are faced with this general question, okay, given this mechanism, these are joints in different directions. And the way the mechanism is made, the links themselves may be shaped very oddly. Now, how do you define the parameters of this mechanism? Okay, that is not very trivial. That is not very simple for a spatial mechanism. So, but fixing this, saying that let us, instead of looking at the physical link, let us replace it by this single common normal, simplifies it to a great deal. You don't, the complexity, the shape of the link doesn't really matter. Okay? An infinite number of links will give you exactly the same motion, provided the relationship between these two joint axes are the same. So what is done by this is it keeps the same relationship between joint axes as the original physical link. You need only this particular line for that. So that is minimal in a sense. Okay? So that is one of the big steps that is taken in kinematics in spatial mechanisms. And then Dynamite-Hardenberg notation is a standard way of doing things, not necessarily a minimal way, but you need to have a convention and you need to stick to that. So you need to develop a convention. This is one of the standard things. Each of you can develop your own convention. There is no problem with that. Only you have to stick to that. Any other question? So, given the cylindrical manipulator, will you be able to do this? So take it as a homework. Okay, look at the cylindrical manipulator and try to do this. That is similar than this. Or any one of them. Cartesian is very trivial. cylindrical, SCARA, spherical. You can do it on this. Out of them, actually what we have seen here is more complex. The number of solutions are more for this than the others. Yeah, if there are no more questions, thank you once again.